Now let's look at the state space analysis. So for a system described using the equations x dot is equals to ix plus be and u is equals to cx plus de. So over here e is the input and u is the output. So we can assume that this system represents a controller whereby e is the input, e is the error, and u is the controller output. So in this system, the functions x and e and u are in terms of x. So sorry, in terms of t. So we need to apply Laplace transforms before we can do substitution of forward, backward, and trapezoidal techniques. So if we apply Laplace transforms, we will get s times capital X. So now this x is a function of s. So s times x plus a times x plus b times e. So e is also a function of s. And then u, capital U, which is also a function of s, is equal to c times x plus d times e. Now we can use the substitutions that we obtained using forward, backward, and trapezoidal techniques and substitute in place of s to convert it into a z form. So for the first one, the forward rectangular rule, we got a s here, so we can substitute s is equals to z minus 1 over t. So when we substitute, this is what we get, and the second equation u will remain the same. Now we can further simplify this and then obtain a function in terms of k. So this will be z times x minus x is equals to t times a x plus t times b e. So z times x will basically become small x of k plus 1 because z times x of k will be x of k plus 1. So we got small x of k plus 1. So now this is a discrete form minus x of k because minus 1 times x. So minus x of k is equals to t times a x of k plus t times b e of k. And we just want x of k plus 1 on the left hand side and we take x of k to the other side. So we will get in a simplified form I, which is identity, plus t times a times x of k plus t times be times e of k, and u will remain the same. So over here u is u of k. So u is equals to c times x plus d times e. So this is the state space formula for the forward rule equivalent. Now the second one, backward rule. So in the backward rule, we substitute in place of s, we substitute z minus 1 over z times t. So when we do that, when we substitute z minus 1 over t times z times x is equals to ax plus be. So now again, so on the left hand side, you will be left with x of k plus 1 minus x of k is equals to ta x of k plus 1 because we have a z on the denominator. So when this multiplies with x, you get x of k plus 1 instead of just x of k plus t times b. So this t and z also multiplies with b and e here. So you get t times b times e of k plus 1. So in this equation, there are terms in k plus 1 on both right hand side and the left hand side. So what we want to do is we want to take all the k plus 1 terms on one side. So when we do that, when we collect all the k plus 1 terms on one side, we get this x of k plus 1 minus t times ax k plus 1 minus t times be k plus 1. and that is equal to x of k. So this x of k will go the other side. Now we substitute for all the k plus 1 terms, we use another variable called w. So we substitute w k plus 1 as that for the left hand side. Now from this equation we can solve for x in terms of w and e. So if we just remove x here, it will be x of k plus 1 minus t times a x k plus 1 minus t times b e k plus 1 equal to, you can say, essentially w of k plus 1. So since all the terms are in terms of k plus 1, we can just substitute k as k minus 1 in place of k, and all of the terms will become, so this will become x of k minus t times a x of k minus t times b x of k is equals to w of k. So now we can take, since these x's are, we can factorize and we can get what I minus ta times x. We can take this the other side, so that will be equal to w plus t times be. So please note that since all of the terms are k plus 1, all these terms are k plus 1, if we substitute k is equal to k minus 1 here, it will become just k. So using that, we just take e the other side, so it will be I minus it times x is equal to w plus t times be. Now we substitute, we solve for x here. So x will be equal to I minus it inverse. So we take this, so this will be in matrix form. If we multiply towards the left, inverse of this will become identity, and so we have to multiply inverse of that on the other side. So we get I minus it inverse times w plus I minus it inverse times t times b, or b times t times e. Now since we got a function in terms of x, we can substitute this here. So over here we said that x of k is equals to w k plus 1. Sorry. W k plus 1. So basically we can say w of k plus 1 is equals to x of k. So x of k is this, so I minus it inverse times w of k plus I minus it inverse times b times t times e of k. So we got this. And we can also use this x in this equation. U is equals to c times x plus t times e. So u is equals to c times x. So you multiply this x in this equation plus t times e. So you will get this c times I minus it whole thing inverse times w plus, in brackets, d plus c times I minus it whole thing inverse times b times t, then whole thing multiplied by e. So we got u as this. We got w of k plus 1 as this, and u of k as this. So these are the state space descriptions of the backward rule equivalent. So when we apply the backward rule substitution of S, then this is what we get. Now the third one, for the trapezoidal or bilinear rule, the Z transform equivalent can be obtained using as this. So over here we substitute in place of S 2 over t into z minus 1 over z plus 1. So we substitute that in place of S. So we got this equation. Now if we expand, we get z minus 1 times x is equals to it over 2 times z plus 1 times x plus bt over 2 times z plus 1 times e, and u is basically the same, cx times ce. Now if we change it to time domain or in discrete form in terms of k, we will get x of k plus 1 on the left hand side minus x of k, which is this, is equals to 80 over 2 times x of k plus 1 plus x of k, since this is z plus 1, plus bt over 2 times e of k plus 1 plus e of k, since this is z plus 1 multiplied to e. Now solving, if we collect all the k plus 1 terms on the left and define this as w times k plus 1. So if we collect all the k plus 1 terms on the left, we will have x of k plus 1 minus it over 2 times x of k plus 1 minus this bt over 2 times e of k plus 1, and that will be equal to this it over 2, sorry, this x of k will come here, so x of k plus it over 2, so this will be plus here, so there is an error, there will be plus here, it over 2 times x of k plus bt over 2 times e of k, and we equate that to root of t times w of k plus 1. So this root of t is just a scaling factor that is applied here to scale this. So it's nothing more than just like scaling w of k plus 1. Now we can now solve for x. We can now solve for x by equating this equal to this left hand side. So in a similar way, this left hand side is equal to this root of t times w of k plus 1. So if we solve that, and instead of k we put k minus 1, so all of this will become x of k, e of k, and this w of k. What we will get is, so this will be I minus it over 2 times, so I minus it over 2 times x of k. So instead of putting x of k, we can just simply put x here to make it simple. So I minus it over 2 times x, which will be this side, minus, so this minus will go on the other side. So we will have on the other side equal to root of t times w plus bt over 2 times e. Now x will be equal to, you take the inverse of this, so we multiply the other side with the inverse of this, so this will be I minus it over 2 whole thing inverse times root t times w plus I minus at over 2 inverse times bt over 2 times E. So now X is this whole thing. Now, so since root of t w k plus 1 is equal to x of k, so I can just write this whole thing here. So root of t times w k plus 1 is equal to xk plus it over 2 times xk. So that will be I plus a t over 2 times x k plus b t over 2 times ek. So now in place of xk I can substitute this. So when I substitute this, what I will get is this equation 5.13. So this x, which is this whole thing, so x is equals to I minus it over 2 inverse times root t times w plus I minus it over 2 inverse times bt over 2 times e. So this whole thing I can substitute here, and when I do and I multiply root t this side, then I will get this equation 5.13. So you can work this out yourself. So w of k plus 1 will be I plus it over 2 into I minus it over 2 inverse times wk, and then I minus it over 2 inverse times b root of t times ek. So that's what I will get. And then uk, again, in place of x, here we can substitute this x. So uk will be this whole thing root of t times c times I minus it over 2 inverse times wk plus this whole thing d plus c times I minus it over 2 whole thing inverse times bt over 2 times ek, e of k. So wk plus 1, I get it in terms of wk and ek, and uk also I get it in terms of wk and ek. So to generalize, so for continuous time described by x of t dot, so x dot of t is equal to a times x of t plus b times e of t, and u of t is equals to c times x of t plus d times e of t. A discrete equivalent at sampling period t will be described by the equations. So instead of x dot of t, I will use, over here we get w of k plus 1. Since for both backward and trapezoidal, we were able to get wk plus 1 on the left hand side is equals to, so this whole equation we can write it in terms, we can give it a name phi times wk plus gamma times e of k, and u of k is equals to h times w of k plus j times e of k, where phi, gamma, h, and j are given by, so phi for forward rule is given by I plus it. For backward rule, it was given by I minus it inverse times b times t. And for bilinear, phi, which is here, it's given by I plus it over 2 into I minus it over 2 inverse. So for bilinear rule, this is what we get as phi. Gamma, for forward rule, we get it as bt. For backward, we got it as I minus 80 whole thing inverse, and for bilinear or trapezoidal we got it as I minus 80 over 2 inverse times b times root of t. So this is my gamma. H for forward, H will be C. For backward, H will be C times I minus 80 inverse. And for bilinear, H will be this quantity here, which is root of t times C into I minus 80 over 2 whole thing inverse. And J for forward, since this equation won't be affected, J will be D. For backward, J will be D plus C times I minus 80 whole thing inverse times BT. And for bilinear, we got J as this quantity, which is D plus C times I minus 80 over 2 whole thing inverse times BT over 2, which is this. So that's how we got those for forward, backward, and bilinear rules. We got the values for phi, gamma, h, and j. So this is the discrete version of the continuous state space equations.